Hello everyone. Festival seasons are near and there are lots of flash sale going on. The flash sale says that there are only 50 iPhone 14 pieces available or there are only 10 MacBook Pro availables. And then what people do is that they try to click the button to block their iPhone or MacBook Pro. So how does this happen? In this video, I'm going to cover the high-level system design of the flash sale booking part. I'm not going to cover everything in the flash sale. I'm going to specifically cover on how do you get your or book your iPhone or MacBook Pro as soon as possible. So there are lots of people that are trying to book their iPhone or MacBook Pro. They click on buy now. And how does lots of people racing together book in the first come first serve order? So that's the overall idea. And here I'm not going to cover in terms of lots of building blocks. What I'm going to cover is at a slightly low level so that we can compare and see how does the things look like when you use Zookeeper, or how does a thing look like when you use Redis or Kafka or the Sharded database. So we'll see at the low level as well and at the high level to see the bigger picture, and then eventually we'll compare various approaches that which one works best. So we are going to cover total 4 approaches to see which one is better and which one should you prefer whenever someone asks you, maybe in interview or maybe in discussions in both the cases. So let's get started. So the first thing is, let's talk about the requirement first. So the requirement is pretty clear that design a system to sell products on sale. Only 1,000 products are in stock. Do not oversell or undersell. That's very important, because if you oversell, then there is a big problem. That, let's say you sell, instead of 1,000 iPhones, you sell 1,001 iPhone, and now you do not even have the stock for the remaining one iPhone. You will have to send the apology mail to the customer, refund the money, and definitely it's not a good publicity. So oversell is definitely a big no. Undersell can still be okay, but what we want is, we do not want to undersell as well. We want that all 1,000 iPhones should be sold, and we should not show out of stock even before reaching 1,000. So that's also important. And lots of e-commerce company, they face challenges, especially with the bots, that they try to buy these phones or these equipments using bots, writing some scripts, and they try to buy lots of such things, and then they sell it in the secondary market. It used to happen a lot back in 2014-15, if I recall. So we're not going to tackle all the learnings and the rate limiting part and all those things. It's a separate video, but here what we are going to do is to have one constraint, that one email ID can buy only one item. So let's say if you have an email ID of anubhav@gmail.com, so you'll just buy one iPhone with this mail ID. So that's a data level constraint which we are going to apply. Of course, there are other layers as well, like rate limiter, which can help you even further, but we are just going to focus on the data layer. And yes, of course, you have very high volume of requests coming in. And again, one important thing is that the constraint is that you need to respond to the customer in 100 milliseconds. It should not happen that all the customer click on buy now or book my iPhone, and then you give a response that, hey, we have taken your request in the queue and we'll analyze all the data and then we'll give you the final result after 1 hour. That's not going to happen. You have to do then and there itself, because we all understand that shopping is mostly impulsive, and it just helps the e-commerce company. If a person has clicked and if they are the first in the queue, why not just let them proceed further? So this is the overall requirement. I'm not going to cover the payments flow, because then what happens is that we start covering the payments flow, and there is a whole system design for payments flow. So we are not going to cover that. We are not going to cover authentication, authorization, and all those things. We are just going to focus, how do we have a constraint that you maintain the stocks and you do not oversell or undersell. Now let's quickly get started with various approaches. So since I have 4 approaches, I'll cover one by one each of those. The first approach is based on an intuition which lots of people have, is to use a queue or a streaming service, so that when you have lots of load coming to you, you put Kafka or any of the producer consumer model, and then you consume at a fixed rate. So that's one thing which lots of people do. So let's talk about what are the advantages and disadvantages of this approach. It will work fine, but there is one caveat, that is, it will not honor the latency of 100 millisecond. So here is how it looks, that you have lots of users. I'm considering 2 users, Alice and Eve. They both are trying to compete with each other by making the first booking. Their requests go to different backend machines. Their requests land to Kafka cluster. They both can land to different partitions of Kafka. And then in the consumers, they will consume one by one. And here what we'll do is that we'll divide the whole stock into multiple small pieces. That is what we'll do, is that instead of having the stock of, let's say, 300, I'll have a stock of 100 plus 100 plus 100. So 3 different machines, each having the stock of 100. So what I have done is that I have divided the bigger problem into a smaller problem, and then each of the consumers is going to consume or is going to maintain the quota of 100. So Alice will land to, let's say, partition 1, that our consumer 1, and Eve will land to partition 2 or consumer 2. And then both of them will get the iPhone if there is enough iPhone available for both the consumer. Otherwise, it will based upon the iPhone available for that consumer or not. So we'll keep on increasing the counter from 1 to 100 for each of the consumers, and if the data is available, we'll give the iPhone, otherwise will not. Now you can see a few problems here, and let me just discuss the problems. The problem is that this queue, number one, it will hinder the latency of 100 millisecond because it's a queue. So what can happen is the first one will reach first and the later one will reach later. Apart from this, you also do not guarantee the ordering as well. So it's not completely fair. What you can say is that it can happen that the shard 1 has finished because there are lots of user and most of them landed to shard 1, and it got finished first, and the shard 2 still has 1 or 2 items left. So you can implement all those consistent hashing and all those things, but they are still based on probability, and it can happen that there will be a race condition. It can happen that the first partition finishes first and then the second partition, and you might end up in a scenario in which you answer to Alice, who requested first that, hey, no stock available, and the next second when Eve requests to get an item, you will give the item to her. So the second thing of fairness gets compromised, but it's still okay. A few seconds here and there, it can happen that you try to book an iPhone, and your friend who tried to book 1 second later, that person was able to book, but you were not able to. So that's still okay. And yeah, you are putting the things into the Redis in memory as a backup, so that if your consumer dies, you are not done. So all the counters are maintained separately by the consumers. So they will have their own counters. So I think this one is pretty much not usable approach, because you tend to publish a data to a queue, but queue can have delays. But I wanted to cover it because what happens is that it gives us the intuition that let's use queue. If there is lots of data, we could use queue, but here we cannot. So we'll move on to the second approach, and then let's see what is the second approach. The second approach is an interesting one, that we have the similar diagram. Everything is same here. We have users, we have backend machines, and we have counters. And basically, you can imagine here, if the counter is less than the allowed limit, then what happens is that you have one big Redis cluster, or in fact, the Redis cluster will have multiple machines as well. So each of these backend machines will make a request of incrementing a counter. So there is a data type in Redis to increment or decrement. So no, I think increment only. So you will increment you can check if it's the decrement is there or not. But here what we'll do is we'll use increment counter. So it will maintain one counter here, and all these backend machines, whenever the request comes, they'll try to increment the value. So this incr command works in a way that it increments the value and then it gives you the incremented value. So that's how it works. If the incremented value is less than the quota, that's 1000, then you proceed further. Otherwise, you can give a negative response to the customer. The way it works is that I'll just quickly share the terminal to show you how it looks. So what I'll do is that I have Redis running on my machine here. You can see I have Redis running. And then what I can do is that I'll connect the Redis client here. So actually I have connected it here. And if I set value of counter as 1, and now all I need to do is incr cc, and it gives me the counter equal to 2. If I do it again, it gives counter as 3. If I do it again, it will give counter as 4, counter as 5, 6, 7, 8. It will keep on giving me the next counter. So all these machines can make the request to Redis with this command and they will get the latest value. So it will just work fine for most of the cases. And the thing is, Redis is in memory compared to the databases, so which try to persist as well. And so it just gives us more leverage. But there are some problems as well, which we should be aware of. So before talking about the problem, I think I should just cover a little bit about the how Redis maintains the data across shards. So what happens is that, let's say you try to set data to shard 1 or the machine 1 or node 1, and you try to set the data in machine 2 or shard 2. What would happen? There could be conflicts as well, right? It could happen that you set one value to one machine and then somebody else sets the data to other machine. So the way it works is that they use something called as CRDT, conflict free resolution data type. They try to resolve the conflicts, and it happens in lots of documents as well, like the you try to have a collaborative tools like Google Doc. Actually, Google Doc does not use CRDT, they use some other thing. But the CRDT was built actually for the collaborative documents mainly, that if there are multiple people trying to collaborate with each other, then there will be conflicts, and how do you amicably resolve conflicts? So that's the overall idea. So here, they use CRDT, and one of the things of CRDT is that, let's say you make increment counter to 5 to the node 1, and then you make increment counter to node 2. Let's say to node 1 you made 5 increment counts, and to node 2 you made 3 increment count. So after certain duration they will try to converge, and while converging, both of them will reach 8, because it's an increment counter. Each increment will increase a value of 1. So after some time they will actually add each other. So that's how it happens. So there can be a duration during which the counter 1 is still shows as 5 and the counter 2 still shows as 3. But actually the value was 8, because you need to sum, and they will try to connect with each other to have the background sync and all those things, and to resolve the conflicts. But there will be some lag. So it can happen that you eventually end up in a scenario that you reach eventual consistency. So yeah, that's what can happen here. So you might end up in a scenario in which you can oversell the items. That is, the node 1 is still showing the value as 5, whereas it should have shown you the value as 8. So you end up overselling things. So it can happen here because of this conflict free resolution. And it can also happen, it's although not very important, but important to just be aware that in case of network failures, so it's not exactly the idempotent operation, increment value by 1. If you try to increment value by 1 and due to network failure you don't get a response, then it can happen that that increment value was already done in the Redis, but you didn't get the value. So you ended up increasing the value again. So it might happen that you know, undersell because you have incremented the value in the server, but you didn't get that value. So basically, you make the increment counter, but you didn't get it back. While getting back, you got some error. So in those cases, you might undersell. But that's not, I don't see it very important because the flash sale happen only for 10-15 minutes, sometimes even like, let's say 30 minutes. So we can still tolerate such things, but the oversell is a problem because it gives us the negative publicity. So that's about the Redis, and you can see the advantages and disadvantage of using the Redis. Now I'll cover the third one, and found that this one is very helpful and it will pretty much solve for all the cases. And that is using Zookeeper distributed counter. Now, if you are not aware of Zookeeper, I'm sure you have heard about it because I have been having conversation with multiple engineers, and what I found was that most of them have used Zookeeper in one way or the other. Many times they have not used it directly; they have used in sync with something else. For example, if they would have used, let's say, Apache Kafka, so they would have used Zookeeper. I think around 2020 or 21, Apache Kafka stopped using Zookeeper. They used something of their own. But many of the engineers have been working before 2020 as well. So they have used Zookeeper more often than we think of. The overall design is pretty much the same. You have these users, they are connecting to the backend machines, and then they are trying to get the counter from the Zookeeper, and then if the counter is less than the maximum allowed values, they will make the order. Otherwise, they'll send the rejection response. So that's the overall idea, which we are going to follow here. And let's just zoom in a bit into this thing, that is Zookeeper. How do you maintain the global counter? Because it is all boiling to how do you maintain the counter? Because if you maintain the counter, you should be able to handle the flash sale. So if I talk a bit about Zookeeper, this is how the architecture looks like. That you have multiple clients, they are trying to connect to the server. What happens is that Zookeeper works on the consensus or the quorum mode. So you need to have odd number of backend servers so that whatever the majority says, that's what is taken as in the consensus. So the read operation, they are just from the local copy. So whenever you are trying to do the read operation, but whenever you are trying to do the write operation, what happens is that the client makes a request to the server, and then server finds the leader. So there will be one leader which we will elected among the Zookeeper servers, and then whatever that leader decides, that will be the rule of the law. So you try to do a write operation, that write operation will go to the server, and then that server will contact the leader, and then that leader will try to get the consensus, the quorum, that hey, this is what I'm trying to do. So still you would need the quorum. So there are lots of things that happen. You can check out their documentation, how does the write operation happens. But you get the overall idea that these servers will be in sync with each other, and they use something called as total order broadcast. You can read about that as well. So this is the overall architecture. Now, if we talk about how Zookeeper looks like, and this is one of the links which I found very helpful for this guy. We'll just quickly walk through that as well. So what happens is that we try to create nodes, and these nodes will have some sequence number. Let me show it using the terminal so that it makes more sense to you. So what I'll do is that I have a Zookeeper terminal with me. So I'll first of all start the Zookeeper on my machine. So I'll start the Zookeeper server with 3 nodes. So this is node 1, this is node 2, and I'll just launch the third node as well. And this is node 3. So basically 3 nodes running together. I have also made a video, or in fact a playlist on Zookeeper. You can check out that as well. So I have 3 nodes running with me. Now what I'll do is that I will connect to the Zookeeper server. So this is the command to connect to the Zookeeper server. Now what I need to do is to just create a node in Zookeeper. So I can create node called as CCCC, whatever. I can create a node. And then under this node, all I need to do is to create minus S, which means sequential, then CCCC. How many C's? 4 C's, then S, or any name. So these names are arbitrary. Instead of CCCC, it could be ABCDXYZ. Doesn't really matter. So I'm trying to create this node. Minus S is sequential. So if I do this, you can see node got created, that is with S0000. Let me move it to the top and try to create one more node. So if I create one more node, I get one more serial number, that is 1. If I create again, I get 2. If I create again, I get 3. If I create again, I get 4. If I create it again, I get 5. So this is how the naming pattern of the node is, that whatever the name you have assigned, followed by 0 padded number. So this is how you can generate the auto increment number. So they follow the ordering as well. So each time they will give you the new sequence number, and it will just work fine for you in most of the cases. In fact, it just works fine. And this should be the best solution which you can use. This is the documentation. You can go through it if you want to. They have the document on internals as well. And there was this one link which I have already mentioned. It also talks a bit about how Zookeeper internally works and how the ordering and all those things work. But I have just covered a glimpse of it nevertheless. So that's the overall idea. So we keep on creating the nodes, we get the serial numbers one by one, and it will just work fine. And I think this should be the best solution. But the problem is that Zookeeper is not very popular. So that's the only caveat which I found, in the sense that I've not seen Zookeeper being used independently by anyone. We could use it, but I've not seen it happening. I talked to a few people and I realized that they generally use in coordination with something or the other. But if they use Zookeeper, it will be fine. Also, one problem is that if you throw a solution, especially in interviews, then it will not solve anything, because what will happen is that they would ask that, hey, you have thrown a solution of Zookeeper, but we want to get more out of it. We want to understand what is happening internally. And if you don't fully understand Zookeeper, I would say that, especially in interviews, you can skip it. Otherwise, if you can fully understand it, I have made a playlist. If you can go through it and you can dig deeper into it, you would realize that this will be fine in most. I could not find any limitation whatsoever. It seems to be working okay for us. In fact, there are other solutions as well, ready-made solutions, which will just work fine. I think there are databases which maintain counter and they also can handle such cases. But nevertheless, now I'll come to the fourth solution. And this one is a final solution, and this one you can use in most of the cases. In fact, I would say that you would be using it in your interviews more than Zookeeper or any centralized counter. In the real world, you might just use Redis and you will be fine. Or you might just use Redis with one counter, one instance will anyway work fine. So the problem with Redis was if there were multiple nodes, but if there is just one Redis node, it will work fine. Now you also have Zookeeper as a ready-made solution which you could use. But what happens is that people would want to know more. So for those cases, this is the sharded solution. So here what we do is that this is similar to the solution number 1, that you have, instead of Kafka, you have multiple databases, and each of the databases have their own counters. And whenever a request comes, you will take a modulus or hash or something. So instead of having a total quota of 600, you have divided the quota of 600 into 3 machines. Let's say 200, 200, 200. Or if you have quota of 1000, then you divide among 5 machines. Whenever a request comes, you take a modulus of email ID or the username, and then your request lands to one of the servers. Now, overall you have divided the load among multiple servers. So we are hopeful that we'll be able to handle the counters with the lesser values, because now you have divided the load overall. So that's the idea. You can see the problem of fairness is not there, because what can happen is that the counter 1 would finish before counter 2, and yes, you are using all those consistent hashing and all those things, but still it could happen, right? So you might end up in a scenario where Alice is able to buy something, whereas Eve is not, although Eve would have tried to buy it before. So that could happen, but it's just solve other problems. It does not oversell, it does not undersell, because you have a database with you, and it just maintains everything in order. So companies are generally okay doing that, because if they are fine with, if they are not overselling or underselling, that's better compared to a 1 minute or a few seconds fairness adjustment here and there. So compromise here and there. So that's the idea. You can see that it gives more statefulness to the order. So what will happen is that even if somebody tries to make a duplicate order, you can just check here. So let's say Alice is a bot and she wanted to buy 2 iPhones for her. It would not happen, because you can have a database constraint here as well. So you don't have to have a global database constraint. You can directly have a constraint here. You don't need any other persistence layer. So that's one thing. The other is in case of payment failures, etc. as well. Let's say somebody tries to make an order, and if those things fail, you can add the counter back later. So that can also happen easily. And yes, the smaller shards are easier to handle. It does not guarantee fairness, but that's overall fine. So if we compare all four approaches, then let's see which one is the best one. So we overall discussed four approaches. And the last one is something which you can use in most of the cases, especially if you are in interview world. Having said that, the approach 3 is perfect. So the things which are bad, I have highlighted in red, and things which are not, which are fine, they are in the black color. So if you see the first one, the approach 1 of Kafka, it was not fair, but we said that it is okay, but the latency is not maintained. So you can imagine it to be in red color. The latency is not maintained. And yeah, it does not even prevent the duplicate orders, because if the person tries to click the order twice, or if they want the to buy 2 iPhones, it could happen that you need to maintain one more layer of persistence to check the duplicate orders. So that's one thing which you need to do. I'm not talking about Atmos one and all those things in producer consumer. What I'm talking about is, if actually the person has clicked twice, then what will happen? Now, if we talk about the Redis increment counter, it is fair, because it is giving you the counter one by one by one. But the problem is of undersell, because in case of network failures, it could happen that you increment a counter, you don't get a value. But the bigger problem is oversell, because the Redis can give you the stale data across nodes. So that can happen. And yeah, it does not have a persistence layer. You still have to build some persistence layer separately. So it does not prevent the duplicate order, which was one of the things. And yeah, it definitely guarantees less than 100 ms. If you talk about the Zookeeper, so for Zookeeper, it does everything except for this duplicate order, which you can anyway handle using some other persistence database or something. But it does pretty much everything. You can see that it handles fairness, undersell, oversell, just that it's a ready-made solution, and many times people don't prefer to talk about the ready-made solutions. That's the only problem I see here. And the last one is, you break the things into multiple shards, and it does everything here. So it does not oversell, undersell, because it's a database. So it will maintain the consistency if you want them to maintain the consistency. It will prevent the duplicate orders, because all the requests of a particular email ID will go to one particular shard. And then, yeah, it will guarantee less than 100 ms. 100 ms is more than enough for any database. So it will just work fine. So overall, you can use approach 4, but approach 3 is something which is perfect for many cases. It's just that it's a ready-made solution, and increment will also be fine. It's just that it will give you a stale data. I just wanted to point to a document which I read here, and I'll put the link in the description, that this is the same problem which somebody found, and overall the answer was that this is how the Redis behaves. So the same thing that now imagine if you have two processes on separate machine and they are trying to increment things together, what will happen? So the answer from the company was similar. It's a different company, but the answer is similar that, yeah, this is how Redis is and we have to live with it. So that was a thing which others also figured, and they are also having the similar issues. And rightly so. If you have two different machine and they are syncing in background after certain duration, there will be some inconsistency. So if you are okay with that, it should be fine. But I don't think oversell is anyway desirable. So in those cases, I think having Apache Zookeeper or even having a simpler setup of sharding the counter would be the best. So yeah, I think I have clarified, I have given the reasonings to which approach to use. And I hope this video was helpful. Please like and comment if you really like it. It really makes a difference. Till the next time, bye.